Please welcome Tobias to S4 Stage 2.
Hello everyone, and thank you for joining my talk titled Special Access Features on PLCs, or at this point, Siemens S7 PLCs as an example. We are Tobias Scharnowski, that's myself, and also Ali. He's sending his greetings, but he cannot be here today. When we look at PLCs, since their inception, a lot of complexity was added to those PLCs. Initially, it was mostly hardware-based changes to those PLCs, but now in the 2000s, vendors started focusing more on software as well. And this is also where the S7-1200 PLC, which we will be talking about here in a bit, which was then invented. And shortly afterwards, there was Stuxnet happening. Everybody knows about it. It showed us that on the one hand, PLCs are actually able to be attacked, and also they're in fact attacked. So different vendors had their reactions to those kinds of incidents, and they started integrating different features, security features, into their products. And if we want to lift the level of kind of a, let's say, a bigger system, the security of it to a higher level, we need to make sure that all the components on the system are actually taken care of. And this may not always happen, and some components may be misregarded, and this is what we will be talking about here today. Now let's look at the S7-1200 PLC. It's one of the more consumer-grade, or whatever you could call that, entry-level PLCs, not quite the smallest one, but it's still pretty affordable for researchers to look at. Comes at some $100 a piece, so just make sure not to burn too many. We burned some, and it gets kind of expensive, and you also have to wait for reorders and stuff like this, so cannot recommend. Here we can see the different layers of the PLC. So there are different PCBs on the board, but the top layer, which we were able to see on the previous picture, is what we focus on here. So on the left side, you see a top view of the first layer PCB, which contains all the different components that make the system run. For example, the ARM CPU is on there, the flash chip of the firmware image itself, and different connectivity components as well. If we flip the board over and look at the right side picture here, we can also see a bit of a smaller flash chip, which only has around 4 megabytes of memory, which holds the bootloader code, which we will look at in a bit more detail. What we also did in order to understand the hardware which we are dealing with, we did a decap of the ARM chip itself, and it turns out that it's an Renesas Cortex, ARM Cortex R4 from 2010, and you can also, via the ARM instruction set, if you have code execution on the PLC itself, extract the exact revision number, which we also did here for reference. Here's another top view of the close-ups of different flash chips, anything that's memory related. So if you're interested in that, we have the different components here. And what we also did was we wanted to have an actual look into the PCB itself. So what you can do is actually take an X-ray, rotate it in front of it for a bit. Initially, the image will be less detailed, and then it gets more detailed over time. And what you end up with is such an X-ray 3D model, which you can actually rotate and zoom into, which is part of one of an ongoing projects that we have at Ruhr-University Bochum. Now that we looked at the hardware for a little bit, let's look at the actual software components. So what we see here is the initialization startup procedure of the bootloader code, which is stored on one of the flash chips, as I talked about before. And what the bootloader does is kind of what you would expect from a bootloader. It's initializing hardware of different stages. Initially, it needs to initialize the very low level of hardware, like the nested vectored interrupt controller and the like. And afterwards, it checks the basic integrity of the firmware image itself. One thing of note is that it's only checking a CRC checksum, which guards you against any hardware-related failures or anything like that. It doesn't protect you from tampering, because anybody could set the CRC checksum to anything. It doesn't have a cryptographically secure signature on it. Now something pretty interesting happens in the bootloader process, which we can see. So initially, after some of the initialization of the hardware, it waits for half a second, and then it waits for a specific exchange. And if that exchange happens, it will boot into a special access feature, which we put aside for a second, but which we will revisit in a moment. What it's doing in the general case, if nothing happens in the first half of a second, then it will just start booting the firmware image itself. And this is what we find when we actually look at the other flash chip and the code that's running on it. There is an operating system which is called ADONIS RTOS, which Siemens created, and it holds the real-time operating system kernel as well as different functional components in order to make the PLC and anything that's supported on their run. You could kind of divide the functionality which is on there in two broad categories. One of those is anything that you would also expect from a general purpose operating system. A general purpose operating system has to talk to its environment, so it wants to speak some network protocols, it wants to have some storage on a hard drive or like a flash chip, and needs to access files on there, so it needs to have operating system drivers and things like that. On the other hand, there are the more automation-related services which it supports. For example, there is the implementation of the Profinet protocol, which is a protocol used by Siemens in order to do different configurations of the PLC. Also, the execution of the binary representation of the ladder logic and similar logic, which can be downloaded onto the PLC, is implemented there, which is called the MC7P parser. And other automation-related services as well. Here we can see what this looks as a binary image. Of course, first of all, to kind of find out this information, you have to look at the code which is actually running it. And this is what we did. So you can get an update file, a .upd file from Siemens' website, which is kind of packed and you have to unpack it, or you can try to dump the flash in total, so to get the flat binary representation. It's about 13 megabytes of memory, so not that the least complex of softwares, let's say, and 84,000 functions. You don't get those right away, but if you start doing some automation, do some scripting, I think I created like 50 or so IDA Python scripts to smooth out different parts and rename different components and do some detection automatically. And you end up with different functions that you are able to name and where you can kind of put a tag on this kind of does this kind of does this, to different degrees of detail, as you can see from some of the names that we assigned here. Some are pretty generic or kind of guessy, and others are with more confidence, let's say. Here we have another view which is important when you start looking at reverse engineering firmware. So the software may at some points just start accessing seemingly random addresses in memory. And either it's just a normal address, which we can see here. We can see different ranges of what those addresses kind of mean. And for example, if we were looking at an address that's inside the .text section, for example, then we have code running there. If we were looking at an address which resides in the data section, it would be a global variable. And if it's anything dynamically allocated memory related, it would be the uninitialized section. We have a second kind of view of this, a second type of memory access, the way that the ARM instruction set or any firmware which is implemented on there will talk to its environment or the peripherals residing on the PLC. It will start accessing seemingly magic addresses in memory. And those addresses are not in fact normal memory addresses, but they are routed through to different peripherals. So different devices are interacted with by those memory accesses, either reads or writes, and then in combinations of bits and stuff like this. And if you see such an access and you cannot really know what it's doing, but you would like to know what it's doing, we have some of the regions shown here. For example, if there is anything you wanted to do with serial communication, let's say SPI or I2C interaction, then it would be to the top left corner, the SPI 0, 1 or I2C 0, 1 memory ranges. Or if we wanted to talk to timers, it would be the different iTimer ranges on the top right there. So it gives you an orientation as soon as you look at firmware code as a reverse engineer. Here we can see what happens as soon as the firmware itself boots up. So it turns out it doesn't really rely on what the bootloader did too much. The bootloader already did some initialization, but the firmware redoes some of this before starting the actual ADONIS operating system. But what it's also doing, it's setting up the stacks for different execution modes. For that, you have to know that the Cortex R4 instruction set or the architecture allows to store different stack ranges for different execution modes. So if you hold the program in some specific location, you can refer back to those stack addresses and see what's going on in a different execution mode for a given time. And this is what's set up, for example, and this is something you can use for reference. Different components which are implemented there, which we already mentioned, are here, and we want to look at some of them. One is the ADONIS TCP stack. It's actually using the Interniche Technologies TCP IP core, so they didn't implement their own version of the TCP IP stack, which is good because you don't redo everything, which is probably has a less quality than if somebody specialized does that. So it's generally a good idea. There's also something that every PLC should provide, of course. It's an update process. You can do it via different means. You can do it via the web server or via an SD card. And the web server is just drag and drop of a UPD file, and it will do all the magic to update. And you can also use an SD card at a yard sale price of 250 euros or like $270 or whatever it is for 24 megabytes of memory. It's a great deal, I heard. Another thing that's on there is the mini web server. And as a reference, what we give you here are different undocumented HTTP endpoints, which are actively used in the JavaScript of the web server itself. So they actually use some acronyms and just repeat them, which gives pretty funny names like li or lo. So it's pretty cool of the engineers, I think, to put those names in place. Okay, now let's look at what's happening in this other branch, which we didn't investigate, but which we saw kind of towards the beginning of the presentation, which is the special access feature. So it turns out if you wire up the UART pins correctly, and you see the pinouts here on the top, on the bottom right, you get into a specific mode, and you can trigger a specific mode. And how does it work? So for the first half of a second, as soon as the bootloader of the S7-1200 PLC boots up, it will be waiting for a magic string or a greeting, which is MFGT1. MFG is mit freundlichen Grüßen, which is German for a greeting. What T1 means, we don't know. Also, if it's mit freundlichen Grüßen, we also don't know, but that's kind of a guess as a German. You will be answered with -CPU. And if you see this kind of answer, you know that you have this feature residing on your PLC. Here we can see what's happening inside this additional functionality. You have different options. You can get the bootloader version, firmware version, things like that. You can check different functionalities of the hardware, and you can also perform some low-level updates of flash memory and the like. What we will be focusing on is two handlers. The first one is one that's numerically queried via the number OX80, which allows different modes of updates. It allows you to update the firmware flash. It also allows you to update internal memory. This is one of the two functionalities that you can do. And the other one that we want to talk about here for a bit is the OX1C handler, which actually exposes to you a different layer of functionality by exposing a table of function pointers, basically some metadata about the arguments that it requires, and then you can call it via this to get a second layer of functionality. So they kind of get more space in their numeric 0 to 128 range, and then they can expand that. What's interesting about this is that in the initialization of the bootloader, this table holding all this metadata is copied to internal RAM at that point, and from there it's queried afterwards as soon as you talk to this OX1C handler. And now the question, of course, becomes what can we do with this kind of functionality? We kind of extracted two interesting capabilities there. There are a lot of more capabilities, of course. And here we can have a bit of a recap of the visualization, what the OX1C handler does. So it's basically looking at a table in IRAM and then calls back to the bootloader section. But as an attacker, what you can do is, in the first step, use the OX80 handler to write to IRAM. And where you write is actually this specific table. You inject both the function pointer and you inject some metadata. And then as a second step, you also inject some payload of executable code that you also put into IRAM. So you have something, a valid entry at an injected position that forwards you to your own payload, basically. And the second thing that you will do then is query this one OX1C handler to query exactly this injected new handler. And this gives you code execution, which you control in bootloader mode, so in the highest privilege level that you can get on a PLC. So we have a little bit of a demo of this, and we will show a video. So first one that we want to show is, does this feature actually exist? That's the first question, of course. And what Ali is presenting here is that he's using the client that we wrote in order to communicate, and we see that the -CPU greeting is actually there. And then we can start talking to it a bit, doing some handshakes, and upload a very specific payload. The second one is we want to see whether we can actually access memory on the device using our code. And for this, what Ali is doing here is that he is, first of all, taking the update in its original state and querying some of the bytes on the image itself, and then comparing it to what we can extract from a specifically crafted payload, as we talked about before, and see if that matches. So this is the first stage of what he's doing. So he's copying 128 bytes out of a region that's corresponding to one of those magic handlers of the HTTP server. And what he's going to do in the next stage is then upload the own payload, which dumps the memory as well. So there are some arguments that we can apply to this payload to dump a specific memory location. And now it's going to run. It's waiting for its greeting again. And now it's uploading. We needed to do some encoding on the uploading because for us the serial interface was a bit quirky. But in this case, as soon as you do those kinds of hacks, so to say, then to this transfer, then it works pretty well. So now we got this new file, and we upload it, or like put it into a binary diffing tool, and see if we compare the two. It's exactly matching the contents. So we can actually access the firmware memory from the special functionality that we injected. And then we will have a third game. So we want to, of course, make the PLC do something meaningful. And you may or may not heard of this. I'm pretty sure you have. It's tic-tac-toe. You don't ever want to win in this game, but either you make a child unhappy or... Okay, so this is the handler this is the invocation of the handler that we inject, that implements our functionality. And then if we see the normal thing, we need to upload again. And then we get greeted with, it's going to be a tic-tac-toe field. So now on the PLC, we can talk to it and we can start playing tic-tac-toe. So of course, very skilled way of playing, and now the 8. We actually won. So this is a demonstration of that you can actually, that's our demo video, so we can get back to the presentation. So you can see that you can get some non-trivial functionality to run on the PLC, and you can kind of do whatever you want with it at that point. So another question, of course, which comes up is what else is out there? As a researcher, we looked at the bootloader already, so that got us an entry, a local entry into the PLC. And there are kind of two ways of looking at it. You could either try to do something like a jailbreak, as we did here, that we can execute arbitrary code on the device itself and are not constrained to like the ladder logic and any other functionality that Siemens put in there on purpose. And the second way of trying to get in would be from a remote perspective, which is very dangerous, of course. And this could be done via attack surfaces such as network reachable protocol stacks and the mini web server, for example. We also have the client utility. Just follow our Twitter streams, and Ali will upload those and link to those, I'm pretty sure. Maybe he has done that by now. I didn't check yet. So what are the conclusions? First of all, we learned, of course, PLCs are becoming more and more complex. They need to have different features to stay competitive and so on. We have more complex processes which we want to represent. We also have vendors who introduce security measures. It kind of, from a time perspective, it kind of aligned with the occurrence of Stuxnet, but it's good to see that. We also saw that some legacy access features are still inside some PLCs. We know that it's not only Siemens, but different ones. Some of them are more open in general and don't even try to create this kind of secure boot up environment. So what can we do with this kind of feature? One of the main issues in this case is that Siemens has firmware signature verification inside the normal bootloader update process. Not the bootloader update process, but the firmware update process. And this integrity is not checked anymore as soon as the firmware is actually loaded and the update is performed. Then this kind of cryptographic check is just forgotten, and only like hardware-based failures are checked against. And if we can use those kinds of features, we could upload this any modified firmware version, and we'll just normally boot the PLC. And one of the issues that could come up, for example, is in the supply chain. If somebody got hold of one of the PLCs before it gets to the vendor, you could modify the firmware without any hardware interaction. You don't see it. You will never notice, probably. And this might have any functionality in addition to, of course, what it was on there before. Some attacker will probably not kill all the normal functionality, but will make you believe that anything is working as intended and will probably also be working as intended, and then some foothold could be kept inside the PLC. So one of the big issues, of course, is that the vendor cannot really guarantee that what's coming to the customer is actually the same version of what went out. And this is exactly what firmware verification and signature, cryptographically secure signature verification is aimed at. And this kind of invalidates this whole approach. There is the first reaction to this is remove this kind of functionality. And I believe in that. As soon as something is threatening the customer, you should remove such functionality. The other look at it from a researcher's perspective is that as a researcher, in order to analyze the system and make sure the software on it is as secure as possible, we also need some access to it. So we need some foothold on the device, and this is what we did. We were kind of motivated by, okay, we need some access in order to be able to analyze. but we don't have this access. Let's look for some access. And as soon as you shut down the access to your PLC too much as a vendor, you will make this kind of access a rare commodity. And as soon as you make it a rare commodity, researchers will be disincentivized from actually telling you about it because they lose their own ability to research into the target system. So as a vendor, one thing to think about is, in order to keep the communication with researchers in the best relationship as possible, is that you may want to think about ways of how to give them access in some debugging capability. And you don't want to have this kind of as a special access feature which is just available to every PLC which is in the customer's production line, but you may think about giving such access to researchers in order for them to report back to you any of their findings and make your software more secure in the end. So this is a kind of the main thought that I want to leave you with, that just removing all the access and trying to get everything secure or seemingly secure by just obscuring all your software is maybe not the way to go. And we see this kind of thing where Pwn2Own is now coming to the ICS space, which I really like. I'm also a participant of those. And we actively want to increase the security of the software, and it's more a celebration of finding and fixing those bugs. Because the reality is that any of the software is broken in the end in some way or another, and it's good to start and fix those issues and get started with it, instead of kind of hiding and not like daring to do the step of getting more exposure on the functionality that you implemented and get those issues fixed. And all in all, we can probably agree that there are a lot of things to make PLCs safer. We have heard a lot of talks about those kinds of areas, and this shows that a lot. We have some special thanks to different people. You know who you are. And with that, I leave you, and thank you for attending the talk.
And does anybody have any questions for Tobias? All right, I guess no further questions. All right, thank you, Tobias.
All right, thank you.